All right, so we're on chapter 3 of this book, and again, this is just like the journey to like hopefully not be sued by O'Reilly for reading one of their books out loud. I guarantee you I'm not making any money off of this. This is solely for educational purposes. Um, if you're new, you're probably not, but if you're new, I do this because it makes it easier for me to learn if I'm reading something out loud. It sounds babyish and stupid, but that's just how it is. I, used to do this with Cisco exam textbooks because those are dry as fuck. This book has been a lot more interesting than a Cisco exam textbook, study guide, but still it's fun to interact with people. And I hope tonight, yeah, it's the O'Reilly Ethernet book. Lord Floofin. That's a good name. Uh, yeah, it's an O'Reilly Ethernet book. It's actually here. Let me show you the zoom out a bit. Show you the cover. I think this is probably like an older edition than I needed to get, but whatever, it's fine. Um, it's a really badass fucking animal. I love the O'Reilly animals, right? So this is the book that I'm reading out of today. We're starting with chapter 3. It is called The Ethernet System. So the past few videos that I've done, the past few chapters that we've read have been just the history of Ethernet, basically. Like the history of Ethernet, where it sort of started with Aloha Net and like the original, shit it had going on. Who invented it? I've already forgotten the names, but we had ThickNet originally, right? When we're using this very thick coaxial cable. Had some great jokes about ThickNet going on the last stream or two. So that was cool. And we learned a little bit about like the different IEEE standards of Ethernet. If you could see up here, these days Ethernet is pretty like a lot faster than it started out. We have all these different standards that we could go through again, but we won't because I consider this kind of stuff, since I'm not studying for an exam and I don't need to go through rote memorization. Oh, you know what? We didn't learn this. What am I talking about? I'm sorry. I went to the wrong section. I skipped ahead. We're actually under, I went to chapter, let's see. No, no, no. No, no, no. We're not in the wrong one. No, no, no. Here we go. I must have skipped back too far. Or I just literally don't remember what I studied last. That's great. That's a great sign for my brain. Honestly, I can see myself just skipping over this stuff in a stream. All right, this information's here if we want it. Anyway, we're on chapter 3 called The Ethernet System. This is the part where I just read out of the book to you. So if you're snuggled up in bed, if you're all ready, you got your weighted blanket over you, your hot water bottle at your feet, let's go. It's time to fall asleep. um, okay, second edition is the latest one that's out. If y'all look, if at any no jokes aside, if any of y'all know more than me, which is going to be literally everyone, about Ethernet, please throw some shit in the chat. I would like to have an actual expert on here at some point in time if I can figure out how the fuck to do that with Twitch. I would like to have actually somebody who knows what they're talking about come on and talk, because it's only a matter of time before O'Reilly fucking sues me for reading their book out loud to people. But anyway. Okay. Yeah, Bobby Metcalf, thank you. Thank you for that name. I don't think that covered the 25 gigs per second. Yeah, okay. So this second edition is from 2014. Holy shit, when did they come out? When are they coming out with a new one? Because I do remember last time we looked at the standards and they were not updated in this book. I had to go to Wikipedia and like read them out loud. All the new ones that have come out since, I guess, since this book was published, right? Thank you for the octopus facts. Yep. Very, very solid octopus facts in the chat. Thank you very much. I don't know how to say your name. I'm gonna try it, and it's gonna be McCuber. It's like MacGruber. I hope. I like it if it is. Is John Capobianco gonna make a mind map of this? I don't know how he possibly fucking would, because this is gonna be just like, it's just like a book. I don't know. The Ethernet system. Yeah, 2014 was a long time ago. I would like to see a new one of these out. Actually, that'd be really neat. Shoot. I'll just do a whole other series of streams on it. Anyway, let's start. It's chapter 3, the Ethernet system. All right, boys and girls. An Ethernet network is made up of hardware and software working together to deliver digital data between computers. To accomplish this task, several basic elements combine to make an Ethernet system. This chapter describes these elements, as a familiarity with the basic elements provides a good background for working with Ethernet. We'll also see how the Ethernet system is used by high-level network protocols to send data between computers. I like that. This is going to be an exciting chapter. This chapter discusses the original half-duplex mode of operation, because that's the system that Ethernet began with. Half-duplex simply means that only one computer can send data over the Ethernet channel at a given time. In half-duplex mode, multiple computers share access to a single Ethernet channel by using the CSMA CD MAC protocol. Until the introduction of Ethernet switches, half-duplex was the typical mode of operation for Ethernet devices. Okay. If you've taken your CCNA, this shouldn't be news to you. However, these days, almost all Ethernet devices are connected directly to a port on an Ethernet switch that's operating in full duplex mode and do not share the Ethernet signal channel with other devices. When Ethernet devices are connected to switch ports, the auto negotiation protocol will typically select full duplex mode, in which the original CSMA CD protocol is shut off and the two devices on the link can send data whenever they like. Half and full duplex mode are both forms of media access control and are described in more detail in chapter 4. Cool. All right, so basic elements of Ethernet. 4 building blocks is what we're talking about. We need a frame, which is by definition a standardized set of bits used to carry data over the system. Did that just cut off without punctuation? Looks like it. Okay, so we need a frame. Frames. A standardized set of bits. Well, never mind. I'll go through this and then I'll start complaining. The Media Access Control Protocol, consisting of a set of rules embedded in each Ethernet interface that allow Ethernet stations to access the Ethernet channel in either half or full duplex mode. All right. MAC protocol. Okay. The signaling components, which are standardized electronic devices that send and receive signals over an Ethernet channel. And the physical medium, which is the cables and other hardware used to carry the digital Ethernet signals between computers attached to the network. All right, let's go over it again. We need frames. We need to standardize our bits. They need to be in like standard, what's another word for standard? They need to be in a specified, God, there is no real good word that like means standardized exactly. That's not standardized. I just hate using it. You use it so much in tech, standardization, standardize, whatever. Predefined. Predefined is good. I'm looking for a word, and again, I don't think it exists, but I shouldn't limit myself. I'm looking for a word that's like standardization implies like it is not just rules, but it is like rules that people have agreed upon, organizations have agreed upon. So, like when you standardize something in the tech world, it's basically like, this is something that we've all agreed to use, these rules for this thing. And in that way, when it's standardized, because of that, we will, everything can interoperate together, right? Because we've all agreed that this thing will work this way, all vendors, everybody, so that when we're creating products that will use this technology or whatever, it's all going to operate properly together because we're all operating on we're all on the same page. We're all using the same rules. Yeah, okay, common. Yeah, okay, in common rules, I guess. Or let's see, common set of bits. I don't know. We'll just go with standardized for now. We know what it means now since I just like rambled about it for 10 minutes. All right, so we have a set of bits You know what? I'm liking predefined better now that I'm like thinking about it. All vendors except Cisco. Hey, Cisco invented some of the standardized things, so you can't shit on them too much, but I won't go out of my way to defend. All right, so we have a predefined, a set, a standardized, group of bits that we know we're going to carry data over our system, whatever our system is, right? So we need a protocol to actually do that, and that's the Media Access Control Protocol. So these are our rules. We have like, I guess, yeah, standardized set of bits, predefined, pre-agreed upon set of bits that make up a frame, which are going to actually carry the data over the system. But we have a protocol that is a set of rules. That's what a protocol is, right? So this is going to be embedded in each Ethernet interface, apparently. So to allow, now I don't know what an Ethernet station is exactly. I'm guessing we will learn. Yeah, it looks like we're going into things more in depth as we go on. But all right, allow Ethernet stations to access the Ethernet channel in either half or full duplex mode. All right, so we need a frame, a set of bits that are standardized. We need our protocol. Then we need signaling components. So we need shit that has to send stuff over the network, right? Like, without that, it's like, why do we even have any of this? So we have, our electronic devices that are actually trying to send data over. We've got the bits that will send the data over, the frame. And then we've got the protocol that's going to be the set of rules that allow us to do this. And then lastly, of course, we need to physically do this thing. So we have to have a physical medium. Cabling, right? Cabling and connectivity. All right, so getting into it, the Ethernet frame, that's the heart of the Ethernet system. All right, so the network hardware, which includes the Ethernet interfaces, media cables, and so on, exists simply to move Ethernet frames between computers or there we go, stations. Okay, let's go back up for a second. Okay, yeah, that makes sense. So we're talking about the Media Access Control Protocol, which is just our set of rules that each, it's encoded into each interface that runs Ethernet, which allows our end devices basically to actually access the Ethernet channel. So we can use Ethernet because our interfaces are encoded to use Ethernet. They're encoded with this protocol, these rules that allow us to use Ethernet. All right, so our network hardware exists simply to move the Ethernet frames between our computers, or what we're calling Ethernet stations. A device connected to the network may be a desktop computer, a printer, or anything else with an Ethernet interface in it. For that reason, the Ethernet standard uses the more general term station to describe the network device, and so will we. I already love this book so much more than any fucking official certification guide Cisco Press comes out with. I'm sorry, Cisco Press, but we're with O'Reilly now. We're Team O'Reilly. Fuck. All right. It's just that first of all, the typos are minimal so far, and already in a Cisco Press book, it'd be like 50 million typos, and I'd be raging. Right now, I've seen only a few minor typos. I haven't even pointed them out because I don't care that much about those. All right, so off of that rant. So I got on that rant because like in a Cisco Press book, a lot of the time they'll like just say something and you don't know what the fuck it is, and they don't explain it for like 2 more chapters. Or they'll be like, oh, we'll tell you about this in like 5 more chapters, which granted they do here, right here with O'Reilly. They do that, but they at least explain things a little bit before that, right? Okay, so all right, we're using the general term station. This is the first time I've personally heard the word station used as for another word of like endpoint or, computer. Yeah, your end device, basically. Your access layer device, maybe. I don't know if that's appropriate for an endpoint. Whatever. Anyway, we're using the word station to designate this. The bits in the Ethernet frame are formed up in specified fields. And down here, again, unlike a Cisco Press book, we have the diagram that we're talking about just below on the same page, which is great. So here's our Ethernet frame. We have our preamble of 64 bits. Of course, we have to have the destination and source addresses. So those are 48 bits each. Type length field, 16 bits. And then our data, our payload, anywhere from 46 to 1500 bytes. And then at the end, we have what we always have to have, in this situation, our CRC frame check sequence, just to make sure that corrupt frames are in good shape. All right, so this is our basic Ethernet frame. The preamble was provided to give the hardware and electronics in the original 10 megabits per second Ethernet system some startup time to recognize that a frame is being transmitted, alerting it to start receiving the data. This is what a 10 megabit per second network uses to clear its throat, so to speak. Love that. Newer Ethernet systems running at higher speeds use constant signaling, which avoids the need for a preamble. However, the preamble is still transmitted in these systems to avoid making any changes in the structure of the frame. Interesting. All right. Hey, Andy, how's it going? Welcome. O'Reilly did a Cisco config book before there was a Cisco press, huh? O'Reilly's really the OGs. Wow. I can't tell if some of y'all are trolling. I love Cisco for LLDP, so. Okay. Oh, so an Ethernet all right, Lord Floofin. I'm sorry, I'm reading all these comments out of order. You're gonna have to forgive me. An Ethernet station is so it can be your computer, a switch, or a router. So it's literally anything that's connected to your net. Well, that's probably painting with too big a brush, but so it can be an endpoint or a network device. Is that what we're saying? Endpoint, computer, or switch it. Yeah, see, we're not agreeing totally on the meaning of station. So let's go back up real quick because there we go. So here's where we're talking about station, right? Because, sorry, where was it? Yeah, okay. So we're talking about like the MAC protocol right here. And, you know, we have that set of rules embedded into our Ethernet interfaces that allow Ethernet stations to access the Ethernet channel. So it allows our devices that need to send data to use Ethernet. And then down here, it sort of explains a station. So the Ethernet standard uses the more general term station to describe the quote unquote networked device. So not network device, networked device. And that's what's tripping me up a little bit. Are we talking about endpoints? Are we talking about other like network device, like switches, routers, things like that? Or are we talking about all of that? I feel like if we were talking about all of that, we could just be like the what's it? Why do we have to use whatever? Okay. Yeah, almost have to travel back in time for some of the terminology. You know, that's a fair point. When did Ethernet come out? In like the fucking 80s? Like it's been a million years since then. Sorry if I made anyone feel old with that statement. I apologize. Um okay, so station could be server or client service, but any member on the network. Okay. Client device. A server or a client device, but any member on the network. All right. So it could be any, okay. So networked device actually does make sense to me in that context then. So we're talking about anything participating in the network is what it sounds like. Sending data, basically. All right. I'll continue on with that understanding unless someone corrects me. So we've got our preamble, and that was really mostly useful just for our old 10 megabit per second networks to clear their throats and just prepare the devices on the other end. Hey, I'm sending a frame. Get ready, bitches. But now we're working with higher speeds, so we don't really need that preamble. It's just still there because we don't want to change things around and I guess complicate it too much. So after our preamble, we have our destination address and then the source address, 48 bits each. The assignment of one portion of the address, CCNA material here, is controlled by the IEEE Standards Association. When assigning blocks of addresses for use by network vendors, the IEEE SA provides a 24-bit OUI, organizationally unique identifier. In my head, it's always we. An OUI is assigned to each organization that builds Ethernet interfaces. A manufacturer of Ethernet interfaces creates a unique 48-bit Ethernet address for each interface by using its assigned OUI for the first 24 bits of the address, then assigning the next 24 bits, being careful to ensure that each address is unique. Okay, very cool. I meant that to sound sarcastic. It just sounded like I actually thought it was cool. The resulting 48-bit address is often called the hardware or physical address to make the point that the address has been assigned to the Ethernet interface. Actually, hang on, let me scroll up real quick. Okay. I was going to ask a stupid question, but I will hold it for a moment. Okay, so each organization is assigned its own unique identifier, which goes into what eventually ends up being our MAC address, right? Our hardware address. Which it says right here, right? It's also called a media access control or MAC address because the Ethernet media access control system includes the frame and its addressing. Makes sense. All right. This allows a vendor of Ethernet equipment to provide a unique address for each interface it builds. Providing unique addresses during manufacturing avoids the problem of 2 or more Ethernet interfaces on a network having the same address. This also eliminates any need to locally administer and manage Ethernet addresses. Now, I think some of us know that. Now, they might go into this, but I don't see it like at first glance. So I'm just going to say, I think some of us already know that like you can now have dynamic MAC addresses and like there's the ability to just fucking change that if you want on your PC or whatever. But this is where it came from at least. Okay, so basically, you know, back in the day at least, when you had a unique physical address for everything, you won't, you know, no Ethernet interface is going to have the same address. You theoretically should not have issues with like switching data, you know, where it needs to go based on how switching works, right? Like, you know, destination port, destination address type of thing. Following the addresses in an Ethernet frame is a 16-bit hyperlink field. Most often, this field is used to identify what type of high-level network protocol is being carried in the data field. So, for example, TCP/IP. This field may also be used to carry length information, as described in the mythical chapter 4 that we keep referencing. God, I can't wait to get there. My brain did not absorb any of that. Hang on. So this field is used to identify what type of high-level network protocol is being carried. Okay. Okay, so are we using IP protocol, IP4, whatever? Then yeah, that's going to be in the TL field. Is it TLV? Am I mixing these up or are they the same thing? TLV field? I feel like I'm not. Give me a moment while I eat this stroop waffle. All right. Pretend that didn't happen. All right, after the field can come anywhere from 46 bytes to 1500 bytes of data. The data field must be at least 46 bytes long. This minimum length assured that the frame signals stayed on the network long enough for every Ethernet station in the original 10 meg half duplex system to hear the frame within the correct time limits. If the high-level protocol data carried in the data field is shorter than 46 bytes, then we have to pad it. Okay. Now this is different from my understanding, actually. I thought it was 64 bytes. I thought in order to be Ethernet, it had to be 64 bytes. Sorry, let me catch up in the comments here. Oh, I love this station theorizing. My wild guess is that station can also be used for, quote, any Ethernet speaking device. Ethernet is not specific to routers like OSPF or EIGRP, for example. With routing protocols, you should use a more specific term like router. Okay. And with Ethernet, you can just say station whenever two devices are communicating. I mean, that makes sense, right? Yeah, I like how you put that. Like, you know, routing protocols are specific to routers or devices that route, right? But when we're talking about a protocol that can be used by all sorts of different devices on a network, that might have just been where station came from. Okay, not TLV. Oh, thank you, McCoover. So the 64 bytes I'm thinking of is the 48 byte payload. Ah, see, that's where I missed it. Hang on. Okay. Yeah. See, I was thinking like the whole entire thing, but right here, of course, if I were paying enough attention, I would have realized that we're talking about just the data field. So this is obviously, the 64 bytes I was thinking of has to do with like the entire Ethernet like packet, right? But right here, we're only talking about the payload portion. I don't know if payload is actually the appropriate term to use here, but it's just what I think of when I think of the data portion. But yeah, the data within that frame that's being sent has to be at least 46 bytes. So McCoover pointed out 64 bytes that I was thinking of is actually that payload plus the 16 bytes for the headers. Actually, wait, hang on. Scroll up. All right, bits. Yeah, okay. So let me just do some totally simple math, not in my head. But yeah, this is gonna, okay, so this is gonna add up to basically what we need it to be, right? 16. Yeah, I don't know. That's 46. No. Yeah, it's 46. So all of these added up right here. I'm just doing math because I want to figure out like what the hell I was thinking. So these are all in bits, obviously. Oh no, we've got bytes right there. Hang on. Hang on, hang on, hang on. I'm literally just adding up the bits. I'm sorry. I should be able to do basic math. I am a woman in my 30s, but you know how it goes. Yeah, okay. So we've got, all right. Okay. So you got all these up in like your minimum. It's driving me crazy. I'm sorry. I want to know the right answer. All right. I'm not going to do the math right now. It should be easy for me, but sitting here and thinking in front of a live stream is not the smartest thing to do. All right. Someone else do the math for me. But see, we've got, all right, this is what tripped me up because, like, right here, we're talking bytes and everything else is bits, right? So these add up to a certain number, but then you need to multiply, like, whatever you're thinking of for your data. Like, okay, if our minimum's 46, I think, like, how many bits is that? That's like 300 something bits plus whatever. Like, I just got bored with the math, to be quite honest. Like, 300 something, 60 something bits, with your minimum of 46 bytes, right? Plus all of these, what does that add up to? And then I realized, like, I don't really care, and it's not that much of a concern at the moment. Okay, 28. What is the 28 coming from, though? Yeah, all right. Yeah, okay, never mind. I see it now. Look at the comments. McCoover's got it. We've got header fields and octets. Yeah, okay. So how many octets is this? So we've got 8 plus 6, right? I'm just dividing these by 8 because bytes and bits, right? So plus 2. Am I stupid? Hang on. 64 bits is 8 bytes. 48 bits is what? 6 bytes. 8 plus 6 plus 6 plus 2 plus 4. Crazy. Can I do elementary school math? Yeah. Yeah. 28 plus 46. No, it's not 28. It's not 28. 8 plus 6. We're going to do this one by one, right? Okay, we're all smarter than a fifth grader. 8 plus 6 is 14, plus 6 is 20, plus 2 is 22, plus 4 is 26. And then what do you get when you add 26 to 46? That's not 64. What? That's not 64. 26 plus 40, or plus shit, I've lost it. Yeah, it's 26 plus 46 is 72. What am I missing about Ethernet? That, this is silly because they're probably gonna fucking explain it right down here. So where are you getting so 8 plus 6 plus 6, right? Plus 2, that's 22, and then you add that. Are we not counting the CRC? Like what's the deal there? Because I'm seeing like a 22 we're talking about in the comments. But shouldn't it be 20? Shouldn't, like, adding up all the headers, not counting the data, right? Like we should be at 26 bytes, right? Oh, we don't count the preamble. Why don't we count the preamble? Because it's part of the frame. Man. So we don't count the preamble as part of our total. Did it say that here and I just... the high-level protocol is shorter than 46 bytes. I hate this because it should be easy math and it's just not, because I don't understand. Because that's the cough. All right, fine. All right. Let's go back up. I'll stop this in a moment, but it's bothering me. Preamble doesn't count. All right, so let's forget about the preamble. We've got 6 plus 6 plus 2. All right, plus 4. Wait, that's not right. Is that right? So we're not counting the preamble. Okay, 48 bits. 48 bits is 6 bytes. So we have 12 bytes plus 2 for 16 bits. So 14. Plus another 4 is 16. Okay. Ah, there we have. That's still not what I wanted to be. 46 plus 16 is 62. We're 2 bytes short. We're 2 bytes short. But you're right. They're probably going to fucking explain this in like the next paragraph. I'm sorry. 18 plus 46. Where are you getting the 18? Where's the 18 from? So we're not counting the preamble, right? So we've got 6 times 8 is 48, right? we got 6 bytes right here, right? Am I insane? 6 bytes plus 6 bytes plus 2 bytes is 14. Oh, yeah, I can't do math. There you go. 14 plus 4. Thank you. All right. 14 plus 4 is 18. Thank you to everyone who spelled out the elementary math to me in the comments, in the chat. I think I'm probably like dating myself, whatever the term is, by saying comments instead of chat. Thank you. Yes, you are correct. Dot 1 bit. Thank you. All right, fuck. So all of that garbage was just to say. So we don't count the preamble, right, in our frame size. So we're just adding this shit up, and if we're using the minimum, right, 46, when we add our 48 plus 48 plus 16 plus 32 to 46 bytes, then we end up getting 64 bytes as our minimum size. So that's why they say, 46 is the minimum. Or rather, yeah, I mean, 46 is the minimum because you have to have a 64 byte frame in order for it to be Ethernet. All right. Whew. Math. All right, here we go. So finally at the end of the frame, there's a 32-bit frame check sequence. The FCS contains a cyclic redundancy check that provides a check of the integrity of the data in the entire frame. It's a unique value that's generated by applying a polynomial to the pattern of bits that make up the frame, and the same polynomial is used to generate another checksum at the receiving station. The receiving station's checksum is then compared to the checksum generated at the sending station, and this allows the receiving Ethernet interface to verify that the bits on the frame survived their trip over the network system intact. That's basically all there is to an Ethernet frame. All that math. Now that you know what an Ethernet frame looks like, you need to know how the frames are transmitted. This is where the set of rules used to govern when a station gets to transmit a frame comes into play. We'll take a look at those rules next. Jesus Christ, I can't believe that it took me that long to like do 5th grade math. I'm so sorry. Hey, Air Inspiration, hello. It is a book, yes. I would scroll back to the cover for you, but honestly, like, I'll lose my spot. And I'm afraid to do that. I'll scroll back later. But the book is called Ethernet, The Definitive Guide. It is published by O'Reilly. It was written by Charles Spurgeon and Joann Zimmerman. I think I remembered all that correctly. It is the second edition of the book, and I did buy it. I did buy it, O'Reilly. I bought it, all right? Legal tender was exchanged for this PDF. And, shit, I meant to have it, like, right here. I have the hardcover somewhere around here. I have the actual book somewhere. Oh, I'm an idiot. Here. Legal tender was exchanged for both forms of this book, alright? It's very pretty. Look. Is this the second? This may not be the second edition that I bought. I bought them separately, okay? So, like, first I found the PDF, and then I was like, you know what? I want a hard copy. Ah! This is not the second I didn't even realize this when I bought it. This is not second edition like the PDF is. And you can see, hang on. This is horrible, I'm sorry. You can see that only Charles Spurgeon is on here. So Zimmerman is not on here, which means this is an inferior text. Sorry about that. Good thing I've only been reading the PDF so far. Okay. Okay, the MAC protocol. I hope it's appropriate that I call it MAC because I don't want to say media access control every time. I think we were supposed to play a drinking game tonight. Someone suggested that on Twitter, but I didn't think it through. Drink every time we say Ethernet, you'll die. Alright, we're talking about half duplex mode of operation, which is the basis of that original 10 meg Ethernet system. Based on the CSMA CD protocol. It's a set of rules designed to arbitrate access to a shared channel among a set of stations connected to that channel. So if you were here for our history lesson in chapter 1, I think, this would have been like a month ago, probably several weeks ago. AlohaNet was talked about in this book as like kind of like the beginnings of Ethernet in a way. Well, in a way, like it was the beginnings of Ethernet, right? And that's where CSMA CD kind of came from, because the stations between like islands in Hawaii were, you know, sending messages to each other, but data was colliding and like it would get all garbled and fucked up. So they had to find a way to send messages without collisions. So here we are, CSMA CD. Note that today most stations use full duplex mode, which provides a dedicated channel between the station and a switchboard. However, to understand the Ethernet standards and Ethernet operation, it's useful to know how the original half duplex system functions. This is so cute. They just like looks like a lemur or something. Just the outline of a lemur right here to delineate this text. It's still possible for a station to use half duplex mode when connected to a switch port at 10 and 100 megs per second over a twisted pair cable. However, higher speed media systems support full duplex only. The way the MAC protocol works is fairly simple. Each Ethernet-equipped device operates independently of all other stations on the network. There's no central controller. Stations attached to an Ethernet cable and operating in half duplex mode are connected to a signaling channel that, because it is shared, requires the use of the CSMA CD mechanism to control access. All right, I'll stop eating. I'm sorry. There you go. Yes, Makoom, I should drink every time I screw up math. I would probably die. Drinking game. Drink every time I screw up math. I feel like that's fair, you know? Okay, so everybody's independent of everybody else. This is the MAC protocol. Everybody's independent of everybody else. There's not like a centralized anything going on. Devices that are attached to the Ethernet cable in half duplex mode are sharing a channel. And so they have to use CSMA CD because that's the collision detection, collision avoidance protocol, and does literally what its name says it does, right? Full duplex mode uses a dedicated link between stations that operates in both directions simultaneously, so there's no need to control access to that link. I feel like we've read that like 5 million times by now. Ethernet uses a broadcast delivery mechanism in which each frame that's transmitted on the shared channel is heard by every station. While this may seem inefficient, the advantage is that putting the address matching intelligence in the interface of each station allows the physical medium to be kept as simple as possible. On an Ethernet system, all that the physical signaling and media system has to do is accurately transmit bits to every station. The Ethernet interface in the station does the rest of the work. So, yeah, very simple. Ethernet is simple. Ethernet signals are transmitted from the interface and sent over the shared signal channel to every attached station. To send data in half duplex mode, a station first listens to the channel, and if the channel is idle, the station transmits the data in the form of an Ethernet frame. I'll read this in just a minute. As each Ethernet frame is sent over the shared signal channel or medium, all Ethernet interfaces connected to the channel read in the bits of the signal and look at the second field of the frame, which contains the destination address, as we saw before. An interface compares the destination address of the frame with its own 48-bit unicast address and any multicast addresses it's been enabled to recognize. An Ethernet interface whose address matches the destination address in the frame will continue to read the entire frame and deliver it to the networking software running on that computer. All other network interfaces connected to the network will stop reading the frame when they discover that the destination address does not match their own unicast address or an enabled multicast address. All right, so up here it says the Ethernet standard uses, quote, frame, although the term, quote, packet is also used by those who are not trying to be precise in their usage. Packet is reserved for describing the data transmitted at layer 3, the network layer, by those who wish to preserve the distinction between layer 2 and layer 3 functions. That sounds hoity-toity. Only people who wish to preserve the distinction between layer 2 and layer 3. It did kind of weird me out when somebody used packet when they were talking about something not layer 3, though. I have to say, I have heard it, and it's like, you know, the CCNA in me is like, "Ooh, what are you saying? That's incorrect. What kind of an engineer are you?" But of course, you know, that means nothing. Of course, it was a good engineer. Okay, so basically we have, you know, data being sent out, frames being sent out on this system, on this layer 2 domain, basically. I mean, a lot of us, I assume, have CCNA knowledge. I don't know, but yeah, like we're sending, this just described like basically, at least for me, what I learned in CCNA, like at the very beginning, how switching works. Like they basically tell you switching works this way. Like how do I say this? Um, in your CCNA studies, at least, well, I took the older one, the version before the one that's out now, but um, they describe switching to you as how Ethernet works. So it's really they're describing how Ethernet works to you as if that is the only way switching works. Which, I mean, it's understandable because like Ethernet is extremely common. Um, so obviously you want to learn that, but I don't know. This is the only way that I ever knew that switching worked, right? All of this is like extremely familiar to me. So I just think it's interesting because I don't know, it's a different perspective for me, right? Still getting out of like the very rigid CCNA headspace. Older versions of wireless use half duplex for reals? Huh. Well, I mean, they talk about channels and shit, so I guess you just listen over like a radio frequency channel instead. Interesting. Okay, multicast and broadcast addresses. Fun, 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 fun. The Ethernet delivery mechanism also supports multicasting, which is more efficient than sending the same frames to multiple recipients. Okay, that makes sense. Not everybody is going to get the frames that are not destined for them, right? A multicast address allows a single Ethernet frame to be received by a group of stations. And applications providing streaming audio and video services, for example, can set a station's Ethernet interface to listen for specific multicast addresses in addition to the built-in unicast or physical address. This allows for a set of stations to be configured as a multicast group, which is provided with a specific multicast address. A single stream of audio packets sent to the multicast address assigned to that group will be received by all stations in that group. Very cool. I always found multicast as a like in theory very fascinating, but like I have not worked with it really at all because, well, we just didn't at my last place of employment. So we just never really had any multicast going on. Never had to troubleshoot it. Never had to think too much about it. Just knew it in theory. Okay, so the broadcast address, on the other hand, the 48-bit address of just all ones, is a special case multicast address. Now, I think that's interesting. It is a multicast address, I guess, by definition, but it's like an everyone multicast address. All Ethernet interfaces that see a frame with this destination address will read the frame in and deliver it to the networking software on the computer. After each frame transmission, all stations on the shared half-duplex network channel with traffic to send must contend equally for the next frame transmission opportunity. This ensures that access to the shared channel is fair and that no single station can lock out the others. Fair access to the shared channel is made possible through the use of the MAC algorithm embedded in the Ethernet interface located in each station. The media access control mechanism for shared channel half-duplex Ethernet uses the CSMA CD protocol. Cool. Whoop. The CSMA CD protocol, now let's talk about this guy. It functions somewhat like a dinner party in a dark room. Love it. One thing I have to say too is that O'Reilly's a lot better about these analogies than Cisco Press. A dinner party in a dark room. That's CSMAC. All right, where the participants hear but don't see one another. Everyone around the table must listen for a period of quiet before speaking. So that is the carrier sense part of CSMA, right? Like CS is the carrier, so it's carrier sense. Once a space occurs, everyone has an equal chance to say something. So that's our MA part of the CSMA CD, which is multiple access. If two people start talking at the same instant, they detect that fact and quit speaking. Collision detection. CSMA CD. Bam. To translate this into Ethernet terms, the carrier sense portion of the protocol means that each interface has to wait until there's no signal on the shared channel before it can begin transmitting. If another interface is transmitting, there will be a signal on the channel. This condition is called carrier. Then we got a little lemur telling us a fact here. Historically, a carrier signal is defined as a continuous constant frequency signal, such as the one used to carry the modulated signal in an AM or FM radio station. Radio system. There's no such continuous carrier signal in Ethernet. Instead, carrier in Ethernet simply means the presence of traffic on the network. The term originates from the Aloha radio system, as discussed in Chapter 1, from which Ethernet was derived. Cute. Thanks, little fact lemur. Another point for O'Reilly over Cisco Press. Cisco Press doesn't have fun animals in their shit. Alright, all other interfaces must wait until carrier ceases and the signal channel is idle before trying to transmit. This process is called deferral. With multiple access, all Ethernet interfaces have the same priority when it comes to sending frames on the network, and all interfaces can attempt to access the channel when it's idle. The next portion of the access control is called collision detection. Given that every Ethernet interface has equal opportunity to access the Ethernet, it's possible for multiple interfaces to sense that the network is idle and start transmitting their frames at the same time. When this happens, the Ethernet signaling devices connected to the shared channel sense the collision of signals, which tells these Ethernet interfaces to stop transmitting. Each of the interfaces will then choose a random retransmission time after which to resend its frames in a process called Backoff. Okay, so when we're waiting during the quiet time for carrier to cease, it's called deferral. We're detecting collisions if we're talking at the same time, and if that happens, we choose a random retransmissions time in which to send our frames again after we've detected a collision. That's Backoff. The CSMA CD protocol is designed to provide fair and efficient access to the shared channel so that all stations get a chance to use the network, and no station gets locked out due to some other station hogging the channel. After every packet retransmission, all stations use the CSMA CD protocol to determine which station gets to use the Ethernet channel next. So fair, so democratic. Very nice. Collisions. If more than one station happens to transmit on the Ethernet channel at the same moment, then the signals are said to collide. The stations are notified of this event and reschedule their transmissions, using that random time interval. Oh, okay. Of course, there's always an algorithm. So the random time interval isn't just random, it's chosen by a specially designed Backoff algorithm. Choosing random times to retransmit helps the stations to avoid colliding again on the next retransmission. It's unfortunate that the original Ethernet design used the word collision for this aspect of the Ethernet media access control mechanism. If collisions had been called something else, such as distributed bus arbitration or DBA events, then no one would worry much about their occurrence. That's a terrible term. Are you fucking kidding me? What's this argument? To most ears, the word collision sounds like something bad has happened, leading many people to incorrectly conclude that collisions are an indication of network failure and that lots of collisions must mean the network is broken. All right. The truth is that collisions are absolutely normal events on a half-duplex shared channel Ethernet and are simply an indication that the CSMA CD protocol is functioning as designed. As more computers are added, there will be more traffic, resulting in more collisions as part of the normal operation of a half-duplex Ethernet system. Collisions resolve quickly. For example, the design of the CSMA CD protocol ensures that the majority of collisions on a 10 megabit per second Ethernet will be resolved in microseconds or millionths of a second. Nor does a normal collision result in lost data. In the event of a collision, the Ethernet interface backs off or waits for some number of microseconds and then automatically retransmits the frame. Half-duplex mode networks with very heavy traffic loads may experience multiple collisions for each frame retransmission attempt. Just each frame transmission attempt. This is also expected behavior. Repeated collisions for a given packet transmission attempt indicate a very busy network. If repeated collisions occur, the stations involved will expand the set of potential backoff times in order to retransmit the data. The expanding backoff process, formerly known as truncated binary exponential backoff. What a mouthful. Truncated binary exponential backoff, which is the expanding backoff process, is a clever feature of the Ethernet MAC protocol that provides an automatic method for stations to adjust the changing traffic conditions on the network. Only after 16 consecutive collisions for a given transmission attempt will the interface finally discard the Ethernet frame. Oh, okay, 16 consecutive collisions. This can happen only if the Ethernet channel is overloaded for a fairly long period of time or if it's broken. Are you asleep yet? I'm almost there. Whew! Okay, if you could borrow an old hub and TCP dump to see all this craziness of the collisions. Actually, that does sound really cool. I've been thinking about getting some hardware to just screw around, but didn't really know what to get and what to do with it, to be honest. But I like that idea. I also was looking at videos earlier, found a guy that just like has an oscilloscope and was just like stripped part of an Ethernet cable, and he had it connected to, I guess, the transmit wires in there out of the twisted pair, and he's reading the oscilloscope and showing the encoded Ethernet juice. Anyway, it was cool. I was thinking about it. Oscilloscopes are probably not super easy or cheap to get, though. All right, hardware. We're talking hardware now. So far, we've seen what an Ethernet frame looks like and how the CSMA CD protocol is used to ensure fair access for multiple stations sending their frames over a shared Ethernet channel. The frame and the CSMA CD protocol are the same for all varieties of Ethernet. Whether the Ethernet signals are carried over coaxial, twisted pair, or fiber optic cable, the same frame is used to carry the data, and the same CSMA CD protocol is used to provide the half-duplex shared channel mode of operation. In full duplex mode, the same frame format is used, but CSMA CD is disabled. Now that we've seen how the Ethernet frame and MAC protocol work, we next describe Ethernet hardware. There are two basic groups of Ethernet hardware components: signaling components, which are used to send and receive signals over the physical medium, and the media components used to build the physical medium that carries the Ethernet signals. Not surprisingly, these hardware components differ depending on the speed of the Ethernet system and the type of cabling used. To show the hardware building blocks, we'll look at an example based on the twisted pair Ethernet media system. All right, let's take a break for a second. Oof. We need some more lemurs in here. It's getting dry. Okay. First, we're going to talk about, so we have signaling components and we have the physical medium that those signaling components signal over, right? So signaling components for a twisted pair system include the Ethernet interface located in the computer, a transceiver, and a twisted pair cable. So an Ethernet may consist of a pair of stations linked with a single twisted pair segment or multiple stations connected to twisted pair segments that are linked together with an Ethernet switch. An Ethernet. I feel like they meant to say an Ethernet system because they say an Ethernet may consist of, whatever. Segments were linked together in the original CSMA CD half duplex Ethernet system with signal repeaters, also called repeater hubs. Modern Ethernet systems are based on Ethernet switches, which typically function in full duplex mode. All right, so in Cisco Press fashion, wow, we've got like a huge blank fucking space down here, and we're talking about figure 3/2, which we cannot see. Must be a big, okay. I was gonna say it must be a big diagram. So here's our diagram that we're talking about in just a moment. A and B. Here's our switch in the middle here. RJ45 style plugs. RJ45 style jacks. All right. This is a sampled twisted pair Ethernet connection. Backup. All right, so that example that we just looked at shows two computers, or what we call stations, connected to a switch using twisted pair cables. Each computer contains an Ethernet interface, which provides a connection to the Ethernet system. The interface contains the electronics needed to form up and send Ethernet frames, as well as to receive frames and extract the data from them. The Ethernet interface is typically provided as a set of chips built into the computer's main logic board. In this case, all you'll see of the interface is an Ethernet connector on the back of the computer. You can also purchase add-on Ethernet interface cards that plug into a card slot in the computer, or an external interface such as a USB port. The Ethernet interface connects to the media system using transceiver electronics designed to work with the twisted pair media. The word transceiver is a combination of transmitter and receiver. I did not know that. What a fun little fact. Transmitter and receiver. Most modern desktop and laptop computers include built-in transceivers for twisted pair connections. A transceiver contains the electronics needed to take signals from the station interface and transmit them to the twisted pair cable segment, and to receive signals from the cable segment and send them to the interface. Scroll down past our diagram here. Here's a lemur. Prior to the integration of Ethernet electronics in laptops and desktop PCs, it was common to use an external transceiver for both twisted pair and fiber optic media systems, which connected to a transceiver port on the Ethernet interface. All right, and then I guess there's an appendix describing external transceivers. All right, so we have another, let's see. No, we're talking about this figure still. 3-2, one more time. 2 stations connected to an Ethernet switch. All right. In that figure, the Ethernet interface in station A is connected directly to the twisted pair cable segment, as it's equipped with an internal Ethernet transceiver. The twisted pair cable uses an 8-pin connector that's also known as an RJ45. Woo! Roll credits. RJ45. Yeah, cool. So RJ45, it's good to know in general. It's an 8-pin connector. So this came in handy for me recently, knowing this. In life, because I've been looking for a new place, moving soon, and in older homes and apartments, I'm talking older, they will still have landline connections, but they'll also have like RJ45 jacks, right? RJ45 jacks, and like, no one wants a fucking landline, right? Like, I don't want a landline. No, who uses a landline? I don't know. I know some people do, but like, come on. I'm looking for a place that has RJ45 jacks. That's what I want, because I've got a gaming PC, I've got stuff to set up, we have a smart home, and I want that stable connection. So I want wired Ethernet. And so, but a lot of people just use wireless for their stuff these days, so they might just need like one jack somewhere for like their access point, and that's it, right? So, my partner and I are going around looking at all these places, and we're like, okay, we have our checklist, right? Like bright, big windows, good commute, valet garbage, and more than one Ethernet jack. But it's hard to tell in these older places. Like, if you're just eyeballing it, you can't exactly, it's hard to tell if it's an Ethernet jack or if it's, I forget the name of the jack that's for a landline specifically, but it's not like an 8-pin connector. It's not an RJ45. I forget what it is. But like, it's hard to eyeball it. So you have to like walk up to it, and sometimes like you want to stick your, we were like sticking our eyes in there. How many pins does this thing have? So good to know. Fun fact. Oh, yay. Okay. All right. Tell me. Phone lines are 2 pairs and use RJ11 connectors. RJ11. All right. Ethernet 1000 base T is 4 pairs in RJ45, but 100 base T, so that's 100 base T is fast Ethernet, runs over 2 pairs, so you can use phone wiring. Oh shit! You can use fast Ethernet over the phone wiring. We don't want fast Ethernet though. We're gamers. I mean, it's not gonna cut it, but it's good to know. You know, it's good to know. Like, I guess some internet is better than none. Yeah, fast Ethernet. Yeah, okay. What sucks is like we wouldn't be able to have anything fat. Yeah, it was actually quite a point of contention, like between us and the places we were looking at. We did finally find a place, but like it must be because everyone's using wireless these days and like no one wants to wire it up, but we could not find a place. We could not find a place that had enough Ethernet jacks. The place we ended up going with has at least 2, like one downstairs in like the living room kitchen area and one in the master bedroom, which is also where like the router modem's gonna go. So like in the closet in there, that's where those connections are. So it's like, does it have to be in like the room that's already gonna have the router? We're gonna have to like, and there might be one like over the counter in the kitchen, but we didn't get to look at it properly, so it might be the RG11, which would be fucking stupid because who moving into a new house is going to use a landline these days? It looked like it could have been a spot for a landline simply because it was like above, like there's a cabinet and then your counter and you've got that like wall space. It was right there, so we're kind of wondering if it's not RJ45. Even if it is, it's not that helpful. It's above the fucking counter. Like, I'm not gonna put my PC there. Anyway, we'll deal with it. We have solutions in mind. But that's my story. Thanks for the stream. Bye. Bye, Rooney. Thanks for joining. Okay. So we're getting through this. I may not finish this chapter in time to like... Holy shit. Yeah, we might be working for a while on this chapter. That's fine. I'll wrap it up. Let's see. Come on. I think I went too far. All right, media components. I'll just finish up this section and then I think I'm going to end the stream. So, cables and signaling components used to create the signal carrying portion of an Ethernet channel are part of the physical medium. The physical cabling components vary depending on which kind of media system is in use. So, for instance, a twisted pair cabling system uses different components than a fiber optic cabling system. All right. A lot of us know that, right? Just to make things more interesting, a given Ethernet system may include several different kinds of media systems, all connected together using Ethernet switches. So you can have fiber optics on the same network as, copper, Ethernet, whatever. It's all good. The design and operation of Ethernet requires that there's only one transmission path between any 2 stations. And Ethernet grows by extending branches in a network topology called a tree structure. A typical network design actually ends up looking less like a tree and more like a complex set of network segments connected to switches throughout wiring closets in a building. Sure, okay. The resulting system of connected cable segments may grow in any direction and doesn't have a specified root segment. However, it's essential not to connect Ethernet segments in a loop, as each frame would circulate endlessly until the system was saturated with traffic. On an Ethernet system composed of segments connected with switches, the switches can run a spanning tree protocol that automatically detects and shuts off loop paths. So, okay, they're going to go into spanning tree in chapter 18. All right. Good little refresher. This is kind of like a CCNA level book. I like it. Like it's a good refresher for me. I want to get into more of the complex stuff with Ethernet, but like as an introduction to it, it's been great. And we are only in chapter 3, so I won't get too far ahead of myself. In the original half duplex system, an Ethernet LAN consisted of network cable segments linked with one or more signal repeaters. Today, Ethernet systems are built using switches to connect multiple network segments together, with all of the segments usually operating in full duplex mode. In full duplex mode, each station has a dedicated connection to the switchboard and doesn't share the Ethernet channel bandwidth on that link with any other computer. Okay, cool. So having gone through, this is where I'm going to stop for now. We're gonna pick it up at network protocols and Ethernet. Maybe I should figure out if there's a way to like mark this somehow. I only have Adobe Reader, so probably not. But yeah, it's just gonna try and get me to buy Acrobat. Anyway, yeah, this has been like we're getting more into the thick of things. Very interesting. Still mostly stuff I know. Some cool little tidbits I didn't really, but still mostly stuff I know from CCNA days. So I'm having a good time. I'm enjoying it. It's very interesting. I'm looking forward to this. Looking forward to the stuff in the future for sure. Okay, so that's it for tonight. I will be back. My schedule at the moment is Wednesdays and Fridays now at this starting at the same time. So that would be 9 p.m. Eastern, 8 p.m. Central. What is that? 6 p.m. Pacific time. This is all US time. Um, I'm really sorry. I don't remember what GMT is at the moment. I don't remember how far ahead of us it is, but yeah, those are the times. I usually tweet about it if I'm going to cancel, and so far it's been last minute, so I apologize for that. I'll be a lot more stable once I move. As I mentioned, I'm moving soon, so I'll be a lot more stable and like reliable with this when I move. So anyway, thanks for hanging in there with me. I appreciate everybody coming out. Please, if you are an Ethernet expert of any kind or just know a little bit about it, please correct me, bother me on stream. I love it. I want to learn. Um, anyway, thank you guys so much for joining.